Okay, hello everyone. I have the task, both enviable and unenviable, of introducing my friend and mentor, Ruth Charney, for this afternoon's next plenary lecture. She received her PhD from Princeton University with dissertation work on homological stability, addressing an important problem in algebraic K-theory. She held faculty positions at Yale and The Ohio State University before returning in 2003 to her undergraduate alma mater, Brandeis University, where she currently serves as Berenson Professor of Mathematics. In the mid-'80s, Ruth turned to the study of Artin groups, where she's made an impact that's been felt internationally in geometric group theory. In important work with Mike Davis on the K-pi1 problem, she developed and deployed the fundamental tools that over time have led to the explosive success of the theory of right-angled Artin groups and the associated cube complexes, a theory that is now unlocking long-standing problems in the study of three manifolds. She also pioneered the combinatorial geometry of RAGs with theorems about automaticity and normal forms. Later, in collaboration with Karen Voigtman, Ruth worked on a so-called outer space, a model space to study automorphisms of RAGs. Most recently, she and her students have launched the study of the so-called contracting boundary for groups and other metric spaces. The idea there is to take notions from cat zero and hyperbolic geometry and, with a little sweat and elbow grease, build a boundary that gives you access to similar dynamical and algebraic applications in enormous generality. When compiling these remarks, I asked several colleagues for their input on Professor Charney's impact, and I was struck by how many of them discussed not only favorite theorems and papers, not only her legendary kindness, humor, care, and mentorship, and the time and thoughtfulness she has dedicated to organizations like the AMS and AWM, but several also cited particular inspiring lectures of hers that they'd been fortunate enough to hear at a critical moment. I have one of those myself. Ruth's talks and surveys are famous for their clarity and depth, and so you've come to the right place today. And with that, it's my honor to turn the podium over to Ruth Charney.
Well, thank you very much, Boone. I'm afraid that's a lot to live up to. So my talk today is entitled Searching for Hyperbolicity. And hyperbolicity has been a central theme in geometric group theory, which is the area I work in now. So what I'd like to do before I jump into the geometry is give you a little quick introduction to geometric group theory because it really is going to motivate what comes later. So what is geometric group theory? Well, I like to think of it as a bridge between algebra, in particular groups, and geometric objects, between algebra and geometry. So what is this bridge? Well, the bridge is built by having your group that you're interested in studying act as symmetries on some kind of geometric object. And then the idea is that the geometry of this object should be able to tell you something about the group, something combinatorial, algebraic, etc., about the group. So you use the geometry to study the group. So what's a group? Well, a group is a set with an operation, and sometimes some of them are very easy to describe. So maybe the set of integers under addition, for example, a set with an operation. But groups arise in many, many different ways in many, many different contexts, and sometimes they come to us in some sort of less obvious form, are not as easy to describe or to understand. So what's this group? All right, well, what I've given you here is something called a presentation. So presentation of a group consists of some generators, which means every element of the group can be written as some products of these generating elements, R and T, together with some equations that these generators satisfy. So if you're not used to presentations, you probably look at this and say, I don't know, what's this group? So let's look at this group in a slightly different way. There's the group again. But now let's look at this group geometrically, all right? Well, I claim that this group is just the group of symmetries of a hexagon. So what are these two generators, R and T? Well, R is just a rotation, a pi over 3 rotation. That's a symmetry of the hexagon. And obviously, if we do it 6 times, we get back to the identity. So that's our first equation. And t will be the reflection across that dotted line. That's also a symmetry. And if we do it twice, we get back to where we start. And it's a quick little exercise to check that if you rotate, then flip, that's the same as flipping and then rotating in the other direction. That's your last equation in that presentation. Okay, but the point is, the philosophy here is that realizing your group as symmetries gives you a picture, literally a picture of your group, okay? Okay, now in geometric group theory, most of the time we're working with infinite groups, not finite groups. And so the geometric objects we're going to be using are also infinite. They're not as simple as a hexagon. So let's just look at 2 easy examples of groups that we're all familiar with. The first one is Z2, the free abelian group on 2 generators. I called the generators A and B. And first I have a presentation. It's generated by A and B, and the A and B commute. Okay, that's easy enough. But now let's think of it geometrically. How can we realize this as a group of symmetries? Well, we can think of it as acting on the plane, preserving the grid, the lattice formed by the integer points, okay? So they access translations, and an element of Z2 translates the entire plane, preserving that lattice. Or another example is a free group on 2 generators, where it's a little harder to draw. There's a well-known action on a tree, and we have to imagine this tree as, it's impossible to actually draw it this way, but you have to imagine all the edge lengths being the same. All the edge lengths are 1. I am not able to draw it that way, but just in your mind, blow that tree up so all the edge lengths are 1. And then if that's the case, then we can take A to be translate the tree to the right, B to be translate the tree upward, and everything is preserved. It's a symmetry. It's preserving the structure and the metric structure as well. Okay, so those are typical examples of something you might see in the context of geometric group theory. All right, so the good news is that every group, literally every group, acts as symmetries on some geometric object. There's something called the Cayley graph, which I'm not going to bother to actually talk about today, but one can always construct something on which it acts as symmetries. Now that something may be kind of ugly and horrible, et cetera, but at least we know there is always something we can realize the group as a group of symmetries. All right, so what does geometric group theory do? Well, it asks that once we have such an action, once we've realized our group as a symmetries of some geometric object, what can the geometry tell us about the group, and what types of geometries? Turns out some types of geometries are much more useful than others for that purpose. So what are we looking for in the geometry that's going to be helpful in understanding the group? All right? Okay, so so what I'd like to focus on today, I really want this talk is mostly going to be about the actual geometry. I'm not going to talk that much about the group theory, so I sort of explain this background as motivation for what we're going to talk about, but I'm mostly going to focus on the geometry itself. All right, so let's start with, oh yes, before I do this, yes, what do I mean by a geometry? I'm referring to geometric objects. So what do I mean by a geometric object? Well, for the purpose of this talk, a geometric object is what we call a geodesic metric space. So a geodesic metric space is a set, x, together with a distance function, d. It tells you, so you're told how far it is between any 2 points. And that distance function, so that's a metric space, okay? But now I want, what is a geodesic metric space? Well, a metric space is geodesic if distances are measured by the length of the shortest path between the 2 points. So if I want to know how far is it from, here to Tokyo, I don't get to travel through the center of the Earth. I have to travel on the Earth and figure out what's the shortest actual path that I can go from here to there. So let's look at the following examples. All right, supposing my set x is just the unit circle in the plane. All right, so just the circle. And I want to know the distance between the point x and the point y. Well, one possible distance is just the Euclidean distance. It's the distance in the plane, right? Is that a geodesic metric? And the answer is no, because there is no path in my circle whose length is the Euclidean distance. If I want it to be a geodesic metric, I have to take the length of that arc as my distance. All right? So always remember that distance is all about traveling in your space. How long will it take me? How far is it for me to travel in my space from point X to point Y? Okay, here's another example. All right, here's my space. My space now is a grid. It's just a grid, all right? And to get from point X to point Y, I have to stay on the grid, and I have to travel along the grid. So for example, if each of those little edges was, say, length 1, I guess the distance there would be, what, 7? 1, 2, 3, 4, 5, 6, 7. The distance would be 7. This is called the taxi cab metric, by the way. You're a taxi cab. You don't get to cut across you have to stay on the streets. So this is the taxi cab metric on the grid. And the reason I gave this example here is it's important to keep in mind that there's not a unique, so by the way, these shortest paths are known as geodesics. We refer to them as geodesics. There's not a unique geodesic in general between 2 points, right? There's lots of shortest paths there, between any 2 points. So geodesics are by no means unique, but they just have to exist. There has to be a shortest path, all right? That's the rule. Okay, so those are our geometric objects. Okay. So now I'm going to be particularly interested in certain types of geometries, and I want to give you a little bit of a history of where this comes from, where some of these ideas come from. So this notion of hyperbolicity. All right, so in the early 1900s, Max Dane studied groups that act as symmetries on the hyperbolic plane. Now, I find how many people know what the hyperbolic plane is? Probably everybody. But just in case you don't, there's a nice Escher drawing up there. And the idea is to imagine that every one of those little which I stole off the internet, by the way. I should, give credit to something. Anyway, every one of those little fish on there are exactly the same size. It's like that problem with the tree. I couldn't really draw it with all the parts being the same. So it's impossible to draw on accurately. So you've got to imagine it's kind of like perspective. So as you go out towards the edges, things that look close aren't, because there's lots of little fish in between one point and another point. They're way stretched out, all right? So for example, if I wanted to travel from some point out near near one edge of this disk and to some other point out near the edge of this disk, I probably don't want to go along the straight line, because that would mean crossing an awful lot of those little tiny fish. I'd be much better off curving in towards the center where I don't have to cross as many fish and then going back out again. Yes? So you see those sort of white curves there? Those are geodesics. It's shorter to curve inward and travel inward and then go back out again than to stay near the outskirts. So you just have to imagine it's as if on the outskirts of that disk, there were tons of hills and valleys, and getting from anywhere to anywhere was way too hard. You're better off curving back towards the center. Okay, so that's what you want to keep in mind. So what did Dane do? Dane was interested, he was studying groups that act as symmetries of the hyperbolic plane, and the reason is that he was interested, these were fundamental groups of hyperbolic surfaces, and he was interested in understanding hyperbolic surfaces and their fundamental groups. And so if you have a fundamental group of a hyperbolic surface, then it acts on the universal cover of that surface, and the universal cover of the surface is the hyperbolic plane. So he had these groups that naturally acted on the hyperbolic plane, and he wanted to understand them better. And what he did is really quite mind-boggling. He used the geometry of the hyperbolic plane to prove things that you would never associate with geometry. So, for example, I don't know, those of you who've been attending the colloquium talks, Avi Wigderson's talks, one of the things he proved was he showed that the so-called the word problem for these groups has a linear time solution. He used geometry to prove that the word and the conjugacy problem for these groups has a linear time solution. I mean, this is sort of an amazing fact, all right? And a lot of other facts about the algebraic properties of these groups, et cetera. This is sort of the pre-geometric group theory, but these are where you can trace the ideas back to. All right, fast forward some 80 years or so, 80, 85 years, and to a very seminal paper of Mikhail Gromov. What Gromov realized is that the only metric property, so hyperbolic geometry has all kinds of interesting metric properties, but that the only property that Dane actually needed for his theorems was the fact that triangles in hyperbolic space are quote unquote thin, and I'll explain what thin is about in a minute. But just intuitively, what is thin about? So you take what's a triangle? You take 3 points in your space and you connect them with geodesics. Well, remember our geodesics all kind of want to curve in towards the center. We were talking about the geodesic lines. Well, it turns out that no matter how far away from each other these points are, these sides of the triangle all curve inward and come close to each other, making for very thin triangles with long tails on the 3 sides, all right? So what Gromov did was he said, well, you know what? We could vastly generalize what Dane did by simply forgetting about all of hyperbolic geometry other than this thin triangle condition. So here's, and as I said, this is this idea kind of launched the field of geometric group theory. He had a lot of other amazing ideas in this paper, but this is the one we're going to talk about today. So here was Gromov's. Gromov introduced a new notion of hyperbolicity, a generalized notion of hyperbolicity. It's sometimes referred to as Gromov hyperbolicity, but these days we just call it hyperbolic. So, okay, so here's the definition. All right, so let's start with our geodesic metric space, X. And take a triangle in X. So as I said, a triangle just means 3 points joined by geodesics, all right? We will say that this triangle is delta thin if each edge of the triangle is contained in the delta neighborhood of the other 2 edges. So another way of saying this is that given any point on any edge of the triangle, it is within delta of one of the other 2 sides. It's either close to, you know, you've got this long side, and it's either close. I think I have they tell me I can use nah, forget it. What I tried to draw there is the delta neighborhood of the two sides going up to the top. All right, the delta neighborhood of that, and you notice that the 3rd side lives inside the union of those 2 delta neighborhoods. So you're traveling along, you're very close to, traveling along this edge, you're very close to another edge, and then when that starts getting far apart, you find yourself getting close to the other edge, okay? So you're always close to one of the other edges, right? So that's what it means to be delta thin triangle. All right, so then the definition of a hyperbolic, Gromov hyperbolic metric space is that there exists some delta such that every triangle, no matter how big far apart the points are, every triangle is delta thin. There exists a delta which works for every triangle. Okay, that's all. That's it. That's the only rule we have. Okay? Okay, so let's look at some examples. All right, so let's take X to be a tree, and imagine an infinite tree. It keeps going on forever, okay? And what do triangles look like in an infinite tree? Well, take any 3 points. I've taken points A, B, and C, and I've joined them by geodesics. I've taken shortest path from A to B, from B to C, and from A to C, right? Okay, so let's take, for example, the edge from C to B, all right? The edge from C to B. How far is that from one of the other 2 edges? Yeah, well, every point on that edge is also on one of the other 2 edges. That is to say, this is zero thin. Delta is zero. There is zero distance between one edge and the other two edges, all right? So this is about as good as you can get, and it doesn't matter how far apart this A, B, and C is, this is always going to be true, all right? Okay, so that's a good example. Let's take the Euclidean plane, just the ordinary plane with the standard Euclidean metric. All right, well, that one's not so good, because just think of, say, right triangles, for example. Make a bigger and bigger and bigger right triangle, and think of the midpoint of the hypotenuse. How far is it from the other two sides? Well, it just keeps getting farther and farther away. There is no delta that's gonna work for all triangles, okay? They just get fatter and fatter and fatter and fatter. Not hyperbolic. Okay, so the interesting ones are sometimes there are examples where some things are thin and some things are fat, but they're kind of interesting. So let's take a product of two trees. Well, if I draw a triangle that lives entirely inside one of the trees, it's zero thin. I mean, it's very thin. On the other hand, if I take a line in one tree, cross a line in the other tree, I see a plane. And as soon as I have a plane, I have bad fat triangles, all right? So that's also not hyperbolic because it contains planes. The minute you contain a plane, you lose control, all right? Okay, so let's go on. All right, so summary, quick summary. We started out with sort of classical hyperbolic space, but that, or more generally hyperbolic, negatively curved manifolds and hyperbolic manifolds. That theory of hyperbolicity, the original classical theory of hyperbolicity, applies only to Riemannian manifolds, nice smooth Riemannian manifolds with a certain kind of Riemannian metric. And this Riemannian metric tells you about the local geometry as well as the global geometry. It's really very detailed. I mean, it's very strong, very limited, okay? Now we move into Gromov hyperbolicity, and we can apply these ideas, or at least we can ask whether something's hyperbolic or not, for any geodesic metric space. We no longer need manifolds. It's very, very general context, and the requirement for hyperbolicity concerns only what I call the large-scale geometry. That is to say, doesn't tell you anything about small things. Supposing delta is, 1,000 miles, then any triangle I could draw in this room, it tells me nothing about what it looks like, nothing whatsoever. It only tells me about triangles that are bigger than 1,000 miles big, right? I mean, so it doesn't say anything about small scale stuff. It tells you only that as you get larger and larger, something is controlled. There's some control over what happens as you get very large. So I want to spend a little more time talking about large-scale geometry. Let's be a little more precise about what we mean by this. Okay, so when you're dealing with metric spaces, when you want to say two metric spaces are equivalent in the normal sense, you would want to say they were isometric, that there's a map between them that preserves the metric on the nose, precisely, right? So that's what it means for two metric spaces to be equivalent, isometric as metric spaces. We don't want that. We want something weaker than that, because we only care about the large-scale geometry. So the way we compare the large-scale geometry of two spaces is to ask whether there is a quasi-isometry between them. So I'm not going to give you a formal definition of a quasi-isometry, but basically it's a map with two properties. One is that it may distort distances, but only by a sort of a bounded amount. There's a linear function that controls how much distortion this function is. And the second condition, if you just have that condition, it's called a quasi-isometric embedding. If you want a quasi-isometry, it also needs to be what I sometimes call quasi-surjective, meaning every point in Y is within bounded distance of a point in the image. There's some bounded neighborhood of the image that covers all of Y. So we say, okay, it's not quite an isometry, but it doesn't distort things too badly, and it's kind of almost surjective. All right. Okay. Here's a more intuitive way of thinking of what quasi-isometry is. I like to think that two spaces are quasi-isometry if, when you stand far enough back and squint, they look the same. all right? So let's try a couple. All right, here's two spaces. The first is our grid that we talked about before, and the second is ordinary old Euclidean space. We'll take a grid and move back farther and farther and farther and squint a little. It's getting closer and closer and closer, and move a little farther back and squint a little more, and pretty soon you're seeing something that looks kind of like a plane. And not only that, these geodesics kind of begin to look a little like the other geodesics, okay? So it turns out these two things are quasi-epistemic. Oh yes, I forgot to say, let's back up for just a second here. Let's see, is it here? Yes. Oh, at the bottom there. So I said I would, if there was a quasi-isometry from x to y, I would use this little symbol. That looks a lot like an equivalence relation, doesn't it? Well, exercise, or if you get bored, go home and prove that this is, in fact, an equivalence relation. All right, if there's an f that goes one way that's quasi-isometry, then it turns out there's some kind of quasi-inverse. It's not an actual inverse, it's a quasi-inverse that goes the other way and is also quasi-isometry. So it is an equivalence relation. All right. Okay. So there's our so the f, by the way, is just the inclusion of the grid into the plane. You'll have to think about what the inverse looks like. Not so obvious. Okay. All right. Here's another one that's easier to imagine. I'll take a tree and I'll insert at every vertex a little triangle. Well, you can imagine if you move far enough away, those little triangles, you don't really notice them anymore, and they look essentially the same. Okay, so there are some examples of spaces that are not isometric, but they are quasi-isometric. Okay. Okay, so when I say large-scale geometry, what I'm talking about is things that are preserved by quasi-isometry. All right, properties that quasi-isometry preserves. That's sort of the large-scale geometry. Okay. All right, why is this? It turns out that this quasi-isometry idea is really important to geometric group theory. So let's go back to our groups for just a minute. The reason is that there's a famous theorem of Milner and Spork, which says that if a group acts, I'm not defined geometrically, but acts nicely on two geodesic metric spaces, then those spaces must be quasi-isometric to each other. Okay, so the first thing I mentioned about groups acting as symmetries on spaces is that there always was such a space. You could always find a space, but of course you can often find many, many, many spaces on which a group acts nicely. And so you might ask, well, what's the relation between those spaces? Well, the fact is that they all must be quasi-isometric to each other, which means that a property that is preserved by quasi-isometry becomes intrinsic to the group itself. It's now a property of the group itself. All right, so from the point of view of geometric group theory, we really like properties that are preserved by quasi-isometry. They are particularly useful in the sense that they are intrinsic to the group. All right? Okay, so, all right. What about this property, hyperbolic, this Gromov hyperbolic property? Well, it turns out that hyperbolicity, Gromov hyperbolicity, this thin triangle property we defined earlier, is indeed invariant under quasi-isometry. That is, if two spaces are quasi-isometric to each other and one of them satisfies this thin triangle property, then so does the other. Now the delta changes. X might be delta thin, and Y would be delta prime thin. You know, it's not necessarily the same delta, but at least there is one. If there's a delta that works in one of them, then there's a delta that works in the other. Okay, so that's good. That's one of the things that makes it useful and powerful for. Yeah. So in particular, so it's preserved by quasi-isometry, and in particular, we could talk about a hyperbolic group. A group which acts on one of these spaces, we can say is a hyperbolic group, and any space on which it acts geometrically will also have this property, okay? All right. So as I said, this was 1980s, late 1980s, that Gromov introduced this idea, and people got very excited about it, and they've been studying hyperbolic groups for 20, 25 years. They're fantastic. We have all kinds of fantastic tools to work with in hyperbolic groups, and lots of great theorems about properties they satisfy. And it's been 25 years, so the question is, what's next, all right? What do we do now? We've really been studying these for a long time. Okay, so what's next? So here's back to our history. Well, what's going on today that I think is really exciting is that there's a lot of work to ask to try to extend the theory of hyperbolic groups to much more, and spaces, hyperbolic groups, to much more general spaces and groups. And the idea is that there are many metric spaces which have some directions or aspects or properties that are kind of hyperbolic, but they don't actually satisfy Gromov's definition. They aren't hyperbolic by the definition, and yet they are in certain ways. And the question is, how can we encode or identify the properties that are hyperbolic and use those to understand these much more general spaces and groups, all right, a much bigger class of spaces and groups. And there's all kinds of interesting work going on about this. I'm going to tell you, well, let's look at an example before I say what I'm going to do. So this is my favorite example because it's just so simple to think about. So we'll start with our space being a torus, wedge, a circle. That is, you take a torus and you take a circle and just glue them together at a single point. That's not the world's best drawing, but you just glue them together at a single point, all right? Now, let's take the universal cover of this space. Well, the universal cover of a torus is just a plane. It's just a flat plane, all right? The universal cover of a circle is just a line, all right? But now we have the universal cover of this thing is a little more complicated. There's not just one torus, but there's a torus, and at each lattice point on the torus, there's a line emanating from it. And after I go one unit along that line, I find another copy of the plane. And then there are lines emanating from that. I can't really draw it, but you have to imagine these planes, and from every lattice point on the plane, there's a stick sticking up, and at the end of that stick, there's another plane, and those planes are all distinct from each other. So I call this a tree of flats. The flats refer to the planes. So a tree of flats, because they are just more and more and more of them going out in all directions, okay? Okay, so let's look at this thing. Well, if I travel there, it has planes, so there's just no way it's going to be hyperbolic because there are these planes in there. So I can draw terrible fat triangles in the planes. All right. So if I sort of think of my triangles or just traveling or whatever along in a plane, in the direction of a plane, I don't feel hyperbolic at all. But if I keep traveling up, or maybe go over a little and then up, okay, I can go a little ways in the plane. The triangles don't get too bad if I don't stay there too long. As long as I keep traveling in sort of an upward or downward direction, mostly along these little edges, it feels an awful lot like a tree. And in fact, if you think of what it looks like to draw a triangle, where your three vertices are at very different heights, one way, way, way up, one over here, and one way, way, way down, it's pretty thin. It's like really thin, in fact. I mean, just try to draw this triangle, okay? Because it's got to go way up, and the only way it can come back down is, I mean, it really is, these triangles are very thin. So in some directions, the horizontal directions, it looks very much not hyperbolic at all, but in the vertical directions, it looks very hyperbolic, okay? So this is a great example to keep in mind when I say there are some, hyperbolic aspects and some not in a space like this. Okay, so what we want to do, so our goal is to somehow encode the hyperbolic aspect of a space and try to use it to, in the way, try to use it to apply techniques from hyperbolic geometry to learn more about the spaces and groups involved. Okay, so that's the idea. How can we capture this and use it effectively? So as I said, there are a lot of people working on different ways of doing this. I want to tell you about a particular one that I've been working on and some of my students have been working on, and a number of other people are now getting involved in, which is using boundaries to capture this hyperbolic behavior. Okay, so let's talk about boundaries. All right, so one way to think about large-scale geometry is to think about what's happened as you go to infinity, right? That's a sort of a large-scale property. So there is a, so we'd like to define the boundary of a space as being the space of rays to infinity. So geodesic rays means just geodesics that go on for infinitely far in some direction. And we look at the set of geodesic rays modulo a equivalence relation, which is if two rays stay bounded distance from each other forever, they're considered to be the same point at infinity. If they're asymptotic, they're considered to be the same points at infinity if they're bounded distance. Okay, so for example, if we just start in the Euclidean plane, and let's just sit at the origin for a moment and think about all the ways we can go to infinity, well, there's basically one for each direction, right? There's a space of directions, right? So what we get, and what the boundary in infinity is a circle, which represents each point on the circle is a direction that you could go to go out to infinity. All right, so we can think of the boundary of the Euclidean space as a circle. That's true of the hyperbolic plane as well. You stand at a point in the hyperbolic plane and look at all the ways you can go into infinity. Again, you just get a circle of directions. All right, okay, so that's the intuitive notion of a boundary. One more. Let's do the boundary of a tree. We like trees. All right, this is a trivalent tree, I guess, except it seems to have a root. So we're going to start at the top there, and we're going to think about all the ways we can start at the top and go to infinity. Well, at each point, we have a choice of two directions we can go to continue out towards infinity, right? And so if you think of the tree as being that red thing, and you're sort of at each point splitting in half the possible ways you can go, and you can see that the boundary is a Cantor set. All right, so in this case, the boundary is a Cantor set. So those are just a few examples of boundaries thought of as all the directions you can go starting at a given point and going out to infinity. Okay, all right, so it turns out that boundaries of hyperbolic spaces, Gromov hyperbolic spaces, are extremely useful, have all kinds of nice properties, and have played a large role in our understanding of hyperbolic groups and hyperbolic spaces. So here's a couple of properties. So the first one is just compactness, namely, if you take X and glue on its boundary, you have to make that precise, but you make a topological space out of X union its boundary, then you get something compact in, oh dear, I guess I'm assuming proper, well, okay, there's a hidden hypothesis here. But anyway, you get something compact. So in particular, this is a compactification of your space, and those are always useful, having some way to compactify a space. The second one, which I kind of like, is a little hard to explain, is the visibility property. All right, light travels along geodesics, all right? So I'm interested in what you can see. I'm standing on a point in the boundary, and what can I see? Can I see other points in the boundary? Well, to see another point in the boundary, there has to be a bi-infinite geodesic that goes from where I'm standing to this other point in the boundary. Well, it turns out in hyperbolic space, given any 2 points on the boundary, there is always a bi-infinite geodesic that goes between them. So I can see everything. This is useful for doing geodesic flows and all kinds of other things that this has convenient is a good property. Dynamics. we have some isometry of X, and we want to know what happens if we apply that isometry over and over and over again. What are the dynamics of this isometry? Well, one of the ways we can study that and classify those is by asking what they do to points on the boundary. Do they fix a point on the boundary? Do they fix 2 points on the boundary? And they're classified as parabolic, hyperbolic, elliptic, according to what they do to the boundary. So that's another use. Finally, all kinds of rigidity theorems. You've all probably heard of Mostow rigidity, whether you know exactly what it says or whatever. It's a very famous theorem, very much uses the boundaries of hyperbolic spaces. Okay, so there's lots and lots of uses. They have all these nice properties and very useful. All right. Here's a key theorem, though, from the point of view of what I'm talking about today, and for the reasons I explained, is this question of quasi-isometry invariance, all right? So one of the things that makes hyperbolic boundaries particularly useful is the fact that they are quasi-isometry invariant in the following sense. If I have a quasi-isometry between 2 hyperbolic metric spaces, then it induces a homeomorphism of the boundaries, okay? So you could actually talk about the boundary of a hyperbolic group because it wouldn't matter which space you picked, you'd always get the same boundary, all right? Any space that it acts on is going to give you the same boundary because of this quasi-isometry invariance. All right, so that's a key property of hyperbolic spaces. Okay, so now let's leave the hyperbolic world and say we want to look at boundaries of other spaces that aren't hyperbolic. All right, well, as soon as we leave the hyperbolic world, a number of these properties start falling apart. So, for example, let's just take the boundary of the Euclidean plane. We have a nice circle at infinity, no problem. It compactifies the plane, that works well. But now things start going down the tubes. So, for example, visibility. If to see what 2 points, to see points from one point at infinity to another, we need a bi-infinite geodesic that connects them. Well, bi-infinite geodesics are straight lines, always, in the Euclidean plane. So if I'm standing at a point at infinity, the only other point I can see from there is the antipodal point on the sphere. It's the only other point I can see. I cannot see any other point on the boundary, all right? So visibility is terrible. Dynamics are absolutely awful. I have this nice action of Z2 on the plane, but what does it do? You take a direction to infinity, you take some ray out to infinity, and you translate it. What do you get? Another ray that's parallel to the one you started with, like those blue ones. Well, if 2 rays are parallel, they stay bounded distance from each other. They represent the exact same point in infinity. In other words, the action of Z2 is completely trivial on the boundary. It does nothing to the boundary. So you're not going to learn anything interesting, dynamical from looking at that. All right, so things start to fall apart. Worst of all, they're no longer quasi-isometry invariant. You can have a quasi-isometry between 2 spaces that does not preserve the boundary. It's just no homeomorphism. The boundaries are just bad. Okay, so that's bad news. So what goes wrong? Why is it that it works in hyperbolic space and it doesn't work in other spaces? Well, just like Gromov realized that all that Dane needed was thin triangles, what we realized is that all you need is the Morse property to make everything work. So let me tell you about the Morse property. So the key property in hyperbolic space that makes everything work and then everything fail when you don't have hyperbolicity is something called the Morse property. So the Morse property is the statement that quasi-geodesics stay uniformly bound, far away from geodesics. All right, I don't want to define quasi-geodesics formally, but just think of supposing I have a quasi-geodesic from space X to space Y. Well, if I start with a geodesic, say a geodesic ray in X, like a ray that goes out to infinity, and perform this quasi-isometry, what I see in Y is now what's called a quasi-geodesic. It doesn't really straight anymore. It kind of does something weird. And in order to get a well-defined map on the boundary, I need to straighten it to a geodesic. Well, this Morse property precisely says there's a well-defined unique straightening, all right? Where without the Morse property, it's amazing how bad things can get. You can get quasi-geodesic that spiral round and round or do all kinds of weirdo things and cannot be straightened, okay? So it is exactly this Morse property that allows you to define this homeomorphism. All right, so the Morse property. Well, we go out, we leave the hyperbolic world, and the Morse property fails. It's hard for me to explain this since I haven't formally defined what a quasi-geodesic is, but it turns out all those red things there are quasi-geodesics. Those sort of, the actual geodesic is the blue line, and those red things are quasi-geodesic, and I could just make those bigger and bigger and bigger, and they'd get farther and farther and farther away from the blue line, and so the Morse property just plain fails. Okay, what about our tree of flats? Does the Morse property hold? Well, I think you could guess after our earlier discussion of geodesics that travel too long in a flat are not going to be Morse, but geodesics that don't are going to be Morse. And in fact, the correct statement is that a geodesic in this tree of flats is Morse if and only if it spends a uniformly bounded amount of time in any plane. So I can specify an amount of time, 10 years, but it can't spend more than 10 years. Well, I guess it's distance, not time, but it can't, go more than 10 miles in any one flat before it decides to leave, okay? So in general, you take an interesting space, there may be many geodesics that are Morse and others that aren't Morse. So our basic, the idea we introduced a few years ago, I'll give some names in a minute, was to supposing instead of looking at all geodesics to infinity, we just look at the ones that are Morse. All right, so we're going to define a new boundary called the Morse boundary, where we only keep track of the geodesics with a Morse property. All right, so there's the say we define it similarly as before, but we only restrict ourselves to Morse geodesics. And let's look at a couple of examples. Okay, well, the bad news is sometimes the Morse boundary is empty. For example, in the plane, there are no Morse geodesics, so the Morse boundary is empty. Oh, well, too bad. But other times, it has lots of, so if the space you start out with happen to be hyperbolic, then every geodesic is Morse, and you get the same boundary you had before, exactly Gromov's boundary. Nothing's changed. On the other hand, you get these intermediate ones where some things are Morse and some aren't, and you can get all kinds of weird spaces as the Morse boundary. It turns out the Morse boundary of the tree of flats is a direct limit of Cantor sets. It's very weird. In any case, the important theorem, so this was what we set out to do, and we were very pleased that we were, this turned out that this was true. So this is some joint work with Harold Sultan and one of my former students, Matt Cordes. We showed that for any so-called proper geodesic metric space, proper just means closed balls are compact. So, so for any proper geodesic metric space, the Morse boundary is well-defined, quasi-isometry invariant, and satisfies basically all the properties you'd like similar to hyperbolic boundaries. So not all of them, but a nice set of properties that are analogous to hyperbolic boundaries. So that's the idea, and our goal is to use this boundary and the techniques that have been developed for hyperbolic boundaries to apply it to this boundary and to learn to use it to study spaces that have some hyperbolic behavior, but not in all directions. So this is still fairly new. We have some interesting initial results, and anybody who'd like to learn more, Matt Cordes just recently posted a survey paper if you'd like to see what we know so far. But hopefully, I'm optimistic lots more will come out of this, so tune in next year.
So we maybe have time for 2 questions. Any questions? Can you please come to the microphone?
I'm a physicist. If you expand Bose-Einstein statistics, it's a quasi-hyperbola. It dominates everything in physics, like what I gave you, everywhere, period.
Good. We like examples of hyperbolic
including prime numbers, which are bosons.
Questions?
Right?
Kim? Yeah, I probably don't need a microphone. Well, it's a big room.
Yes, you do need a microphone.
Right there, Kim.
Yeah, there's a mic right there.
I was wondering if you had a characterization of exactly which finitely generated groups have empty Morse boundary. Of course, you don't have to answer it.
I'm thinking. For groups.
Or for spaces. Or,
Yeah, no, that's a good question. I don't have a characterization of that. I mean, you know,
I mean, should they
make
just
some
be
guesses,
like,
but I don't
Yeah.
have
Maybe
a
for cat
characterization.
zero groups?
So,
Are there-
well, I should say, be careful. I mean, I didn't say this, but as soon as you have a direct product of infinite groups, you're gonna, so I'm really assuming directly indecomposable. Otherwise, you definitely have empty Morse boundary, because otherwise you have planes. So let's assume indecomposable, and then I don't have, beyond that, I don't have a characterization.
Okay. Thank you for the homework. Okay, one more question, Laurie?
Your example of groups are all discrete groups. So
Yes.
I was wondering if this theory applies to Lie groups as well.
You know, I don't know. You're absolutely right, because if I were going to deal with that situation, I would be thinking of lattices in the Lie group. So you know, so what we talk about, I didn't define what I meant by a geometric action. So the Lie group might provide the space on which it acts, is the point. But the group itself would be something like a lattice, because when we talk about a geometric action, we're really talking about discrete groups, and all of this is in terms of that. So Lie groups could come into play, but more as providing, you know, a space on which, say, a lattice acts. I don't know that you could, yeah, so you could treat it as a space and look at its, I don't think it's ever going to have Morse boundaries, is it? Let me think about that. Yeah, I can't think of any, oh yeah, there will be some. Yes, my groups are all discrete is the answer.
Okay, so let's address more questions personally to Ruth, and let's thank her again.